Welcome to our second half of the first unit. The first half of our unit, remember, was called electric charge and Coulomb's law. The second part of our unit is called electric field. We want to talk about why forces exist in the sense of how does an object not in contact with another object how can the object even be aware that there is a force acting upon it? Okay, so this is something that we call action at a distance, and it has bothered the ancients for a very long time. How can the object, say the sun, act upon the earth without actually touching it? So this is a good question, and we know that if we push a table or throw a ball, when we've acted on an object, we know we've acted on it. There's actual contact there. So it turns out that when things are acting from a distance, we might think that there's no way they could influence something from a distant, from that distance. But let me just talk a little bit about pushing on that table. What exactly is happening when your hand pushes on a table? Well, you say, well, my hand is touching the table. My force is coming from the muscles of my arm. The forces in my arm are acting against the table and overcome friction or perhaps gravity, and this table will move. Slide across the floor, or maybe lift it up, or whatever. But there's something interesting about the word touch. What do you mean by touch? Are you really touching the table? So let's look at this deep down and close. So if you really zoom in, of course, down to the atomic level, the atoms in your hand and the atoms in the table aren't necessarily touching at all, but rather the clouds, the electron clouds, are repelling each other. And that's probably a fairly weak thing. You'd say, well, that kind of depends. That depends on what the table's made of and that sort of thing. And I'm just trying to convince you that deep down on the level of the atomic scale, nothing necessarily has to be physically touching anything. The forces that are exerted from your hand to the table are a consequence. The reason the table is able to feel them is because of electricity. There's electrostatic interaction between these atoms. So without getting too into this, just understand that when you quote-unquote push an object, you aren't touching it either. The atoms are making other atoms aware of their presence somehow. And this, in a sense, is action at a distance, albeit a very small distance. So what causes an object to feel the presence of another object? Why does mass know about existing masses nearby? And why does charge know about existing charges nearby? So we don't have that question completely answered, but we do have something called field theories. And in a field theory, we assume that the acting object provides the surrounding space with an awareness of its presence. And this is true for gravity and for electrostatics. Okay, so the idea is this. Mass sets up a gravity field, and charges set up an electrical field. Let's talk, of course, about charges since this is the E&M class. The charges set up a field completely independent of other charges. Okay? Now, I like to think of a field as sort of the aroma of a force, if you can think of that, or aroma of a charge, I should say. It's the aroma of a charge. So imagine you were walking along and you smell trash. You know it's trash. You're like, man, that's trash. Well, it's most likely true that there's a trash can nearby, right? Or some kind of waste facility or something. Okay, now, that smell was there before you came, right? And you actually were able to encounter that smell, but the particles were in the air before you arrived, right? In other words, the smell was already present. It's only until you smell it, though, that you know it's there, okay? Now, if you walk towards the trash can, you'll experience more smell. And as you walk further from the trash can, you'll experience less smell, hopefully. And so that's sort of like the idea here. So the electric field is different from electric force. Okay? Electric field is different from electric force. And I'm going to fill in this blank down here. Electric field is present whether or not the victim charge is present. Okay? So you do not have to have two charges to have a field. You only need the one. Every charge in this universe sets up an electrical field near itself. Okay, now, field and force both start with F, as our book states, but it doesn't mean they're the same thing, right? Think of it as arguing and angry, okay? Arguing and angry. You know that a person can be angry all on their own. It doesn't require two people to be angry. But the word argue is a different story. If you hear the word argue, you can assume there's at least two parties involved, right? Perhaps two angry people, right? Okay, so that's kind of like the idea, the difference between force and field. Field is like anger. It's just there, perhaps. It only takes one charge to have a field, just like it only takes one person to feel angry. So it's almost like it's shooting out of the particle, sort of. And force is like the argument. So force requires another object to sense the first object. So just like it takes two to argue, it takes two to have force. And just like it takes only one to be angry, it takes only one to have a field. Now, how are these two concepts related? Well, they're related through the one interacting. So here's the way it works. The force acting on an object, a charged particle, is going to be the particle's charge times the electric field value at that location. So it's kind of like, in the case of gravity, gravitational field is multiplied by mass to produce gravitational force. And in the case of electricity, electrical field is multiplied by charge to produce electrical force. So that's one way to look at it. Another way to think of it is to divide by Q and to think, oh, this new idea of electrical field is just last chapter's idea of force divided by Q. And Q is the one experiencing the field. And experiencing the force. So if you kind of think of it this way, imagine you're in an argument, right? And then you just walk away, which is often the right thing to do. Just walk away. You leave a very angry person there behind. Now, you're not doing this to make them mad or to manipulate them or their feelings, but maybe you just need a moment. So you step away. Well, when you step away from the argument, the anger's still there. And this is true also for a charge leaving a field. The field's not going to change, or leave, but you can certainly leave the field, if that makes sense. So the field's not going to leave, but you can leave the field. All right, I hope I've drawn enough analogies to help you sort of understand the idea of field. Notice that the units then, because you're dividing force by charge, are going to be newtons per coulomb. Newtons per coulomb for the units. And this is something we always want to do. Every time we develop a new idea, we want to put units on it, right? So the MKSA units would be newtons per coulomb. Okay, now, how do we quantify field? How do we draw fields? Well, turns out that we'll talk about the drawing part first. Okay? So there's 3 rules for drawing a field. 3 rules for drawing a field. Okay, the first one is we use lines. So we use lines to draw a field. And we want to draw them kind of the way we draw force vectors. We want to have them represent both magnitude and direction of the electric fields at a certain location. Okay? And just like the smell near a trash can might be different from the smell away from the trash can, probably is, right? In that situation, you want to be able to sort of draw the smell in various locations. So that's kind of the idea. And as you change locations, the field changes. That's just the way it is. All right, for direction, we're going to assume that the direction will be always tangent to the field line. Tangent to the field line. Okay? And for magnitude, we will look at the density of the drawing of the field lines to make sort of a relative statement about magnitude on a location. Okay, so let me kind of draw a picture. Imagine you have a field. Okay, you might say, what caused these curves? Well, don't worry too much about that. That's actually a big part of this chapter. In this, you'll notice three lines. They're kind of roughly parallel, and what's causing their bending is not appropriate to discuss right now. We're more interested in actually direction and magnitude than we are in why it's turning. So let's say that there are arrows drawn on here. So what does that mean? That means that if you pick a random point, let me use green. Let me say you pick this point right here, point A. Draw your vector, your field vector, in the direction of tangency. So the field vector would point like this. Okay? And if you go over here to this point, you'd see that that point B, has a very similar direction to point A. You can just tell from the tangency there. And then over here, perhaps another one that might have that same general direction is point C. So these are not necessarily all exactly the same direction, but they're roughly the same direction. Okay? All right, so that's kind of how you gauge the direction. So the direction will just follow the path of the blue line. If we come over to here where the stars are, the directions would be something like this. So notice the last three that I drew, which I'll highlight in yellow, these three do not have the same directions, although two of them look kind of parallel. Okay? So that's kind of how you tell the direction. Now let's look at how do you tell magnitude. Well, there's no way to predict actual magnitudes when you're looking at a field drawing. Okay? Okay, so the way we do it is, let's say you pick a point. Let's say point A, maybe a point B, point C. The way we can tell which one's experiencing the strongest of the fields is to look at the density of the field lines surrounding that region. So maybe look at this little region and say, how far apart are these three blue field lines? And you say, well, they're kind of close together. You get over to here to point B, you see the three lines are further apart. You get to point C, they're further apart still. So out of these 3 points, A would have the greatest experience of field, B next, and C last. C would feel the least magnitude of net field there. Okay? So it's more of a density thing. And the only thing you can really do here is compare A to B or compare B to C, but you can't really say, well, A is experiencing 1, Newton per Coulomb of field, and you can't make that prediction without more information. All right? Okay, so that's first, how we draw field lines. Another thing you need to know about drawing field lines is that field lines should originate on positive charges and terminate on negative charges. Now, this is completely historical and arbitrary, but the idea is this. If you have a proton, you should think of it as field lines are radially and spherically pointing out of this object. On the other hand, if you have an electron, field lines are pointing towards this object. Okay? And this is just a convention, just like we usually think of right in math as positive and left as negative, up as positive, down as negative. It's totally arbitrary, but we do need to distinguish between positive and negative charge in this way. We can think of positive charges as emanating a field and negative negative charges as receiving a field line. Now, both objects are emitting the field. This is the hard part to understand. Both charges are producing the field, but the lines are drawn, and it would appear that only the positive one's producing a field, and it looks almost like the negative charge is sort of feeling someone else's field. No, no, no. Both of these drawings represent a single object producing something. So the positive charge is producing field lines that come out, and somehow the negative charge is producing field lines that come in. Now in gravity, masses produce a gravity field, right? They don't produce an electric field, they produce a gravity field. If they're neutrally charged objects, they do not produce an electrical field. But they do produce a gravity field, and that gravity field is always inward. Always inward, from what we know of nature. So we've never been quite too sure if there's any masses that emit field lines that are pointing away from. In other words, we have negative, it looks like negative charges, when we draw mass. We draw the field lines coming towards. Okay? The next thing I want to talk about is what happens when you don't just have a simple proton or simple electron or something like that. And the field lines aren't perfectly radial like that, like poking out like a sphere. By the way, when we drew the proton and the lines coming out, you have to also imagine that the lines are coming out towards you and they're spherically being distributed, okay? Oh, and one more thing. If you pick a point A versus a point B, you can see that the density of the field lines at point A is larger than the density of the field lines at point B. In other words, once you get out to point B, the lines themselves are actually further apart than they are when you're at point A. So this drawing convention is very nice because it also reinforces the idea I spoke of earlier that the further apart the field lines, the less field is felt in that region. So B literally experiences less field, and that kind of jives with the idea that it will encounter a smaller force. Okay, let's talk about point charges. So point charges are like what I drew just a moment ago, pointing radially outward or radially inward. We need to at least quantify what a point charge will produce in terms of field. Otherwise, we'll never get to the complicated stuff. So we're going to say that a point charge produces a field K times Q over R squared. This is the magnitude. Okay? Written as a vector, if you want to include direction, you would say KQ over R squared R hat. So the R hat is that little bracket cos theta sine theta thingy. Okay? Or you can use, like I hat plus, 1/2 I hat plus root 3 over 2 j hat or something. You can have a Cartesian vector, but think of R hat as sort of supplying the direction of E. It supplies the direction of E. And so that is our method of quantifying the field produced by a single point charge. Okay, we already said that whenever the field lines are pointing away, it's because the charge is positive, and whenever the field lines are pointing towards the charge, it's because that charge is negative. This actually now makes sense. So E and R hat being in direct proportion means that if Q is a positive number, and obviously K is a positive number, R squared is a positive number. So if Q is a positive number, right, then we would want that would mean that the charge is a positive charge, right? We would want the field lines to point radially away from the point charge, right? So when Q is positive, we want R hat to point outward, right? And when Q is negative, we want R hat to point inward. So we want the electric field to have the same direction as R hat does. And remember, R hat always points radially outward. Like R hat it means, 1 unit radially outward is what it means. 1 unit radially outward. That's what r hat always means. Okay? So the q then controls the situation. If q is positive, E is positive, pointing outwards radially. If q is negative, then E is negative, meaning it points radially inward. Okay, so hopefully that wasn't too confusing. Maybe when we do the problems, it's a little bit easier. Let's go on to the second bullet. E points away from the point charge if the charge is positive. I already said that. Points towards the point charge if the charge is negative. I already said that. And we can just write this statement. If capital Q is going to act on little q, then it's going to produce the exact opposite force that little q produces on big Q. And either way, it's going to be kq over r squared. I have these backwards, I'm sorry. This is big Q, little q, and then it goes, little q, big Q, and then big Q, little q. This is what I meant to write. We usually put the acting particle first. I'm sorry, we usually put the recipient particle first. So either way you want to look at it. The only difference between the charge A acting on charge B field and the charge B acting on charge A field, the only difference is a direction thing. Okay? And so you'll notice it doesn't even require a second charge. Right? You don't even need a second charge. You just have to have one charge to set up the field. So I guess because there's a lowercase q there, you can just think of this as little q's charge. So little q is emanating a charge. Let's say it's positive. And then out here there's a point, right? It's going to feel, that blue dot is going to feel the presence of Q, right? And then if it's the other way around, as long as this is a capital charge, a capital Q charge, then think of the red dot, little q over here, and let's say the capital Q is also positive. Now little q is feeling the presence of big Q, and the only difference between their the directions of their the only difference between their E vectors is the direction. Okay? But remember, with or without an agent, with or without a recipient, the field's there anyway. Okay? So maybe you don't really even need this statement about Q on Q. All right? But here's my statement about R is always directed radially outward. All right, now let's go to the next comment. Okay, it says that the net field at a point in space is the vector sum of all the fields of all n charges in that area. So if you're in a spot and you're surrounded by different charges, you're going to feel the field of every single one of them, right? So that's natural. You're going to add up all the vectors of the fields around. So we can just simply do what we did with forces. The net field experienced is going to be the vector sum of all the fields impacting that region. Okay, so this just goes on and on. In other words, it's the sum, if there's n charges, it's the sum from I equals 1 to n of E sub I. Right? Okay, now since each of these E1, E2, E3, and so on, since each of them has a different direction possibly, we need like a magnitude and a theta for every single one of them, right? Okay, so this is where it gets kind of complicated. It's probably easier to not use polar. It's probably easier not to use theta, but to just use I hat and J hat. So I just want to remind you that what is I hat and J hat? So cos theta I hat and sine theta J hat, these are what I've been using when I put in the brackets two values. So for example, when I put in root 3 over 2 and I put in 1/2, what I'm really saying is that I'm dealing with 30 degrees angle, because root 3 over 2 is the cosine of which angle? 30 degrees. And simultaneously, sine theta is the sine value of that 1/2 is a sine value of that same angle, 30 degrees. So you can tell that theta is 30 here from the unit circle, right? Okay, so I think it's probably more meaningful just to take the magnitude, which is out front, right? And instead of doing the comma thing, for this example, I'm going to use the I hat and j hat thing. So it's going to look like this. The net field is going to be basically E1 x direction times I hat plus E1 y direction times j hat. And then next we're going to have field E2, E2 x I hat plus E2 x j hat. E2 x, sorry, I meant to say E2 y j hat, and so on. So that if you really wanted to kind of separate this, you could put all the I hats together and separately put all the j hats together. So it would look something like this. So the net field is going to be E1x plus E2x plus E3x, etc. And those are your i's. And then plus, and then E1y plus E2y plus E3y plus dot dot dot, and then those are your j's. Okay? So we always keep the x's separate from the y's. That's very, very important. If you haven't had mechanics, you need to know right now that the x activity and the y activity must be always kept separate. And vectors help us to do that without writing too much. Okay, so I know it says find the net field shown in the diagram below, and there's no diagram below, so I'm going to draw that diagram right now, okay? We're going to assume that Q1 is 2Q, positive, Q2 is negative 2Q, and Q3 is negative 4Q, all right? So sorry, it's a little sloppy. This says Q2 up here. All right, so when we draw the field lines for the vectors, we can draw them all at point K, almost as if K is actually an object, even though it's really just an empty point in space. There's nothing at K, folks. There's no charges at K. We're not doing forces here. We're just trying to see what kind of fields exist at K. We're going to pretend it's like a free body situation, okay? Now, because we have the charge values, because we have the signs of the charges given to us, we can just not worry too much about the whole field lines point towards a negative and field lines point towards a negative charge and away from a positive charge. We don't have to really think about that because when we plug in the 2Q and the negative 2Q and the negative 4Q, that will take care of itself. So we're going to use the idea that the sum of all vectors, we call that the net field, is going to be E1, which is caused, of course, by Q1, plus E2, which is caused, of course, by Q2, and E3, which is caused, of course, by E3. All right? And so we're going to assume all this is two-dimensional also. Nothing's like out towards us. There's no z-axis, whatever. Okay, so this is just going to be KQ1 over R squared. This is going to, times R hat, plus KQ2 over R squared. That's going to be R hat. And then we're going to have KQ3 over R squared, and that's R hat. And the R hats are all different. The R hats are the radial unit vectors. They always basically point from the actor, right? So they all point radially out of the 3 blue dots. Okay, so I'm going to have to index these. This is going to be R1, R2, R3. So unfortunately, they are different unit vectors. Okay, so the good thing is about this problem is that A's are all the same. Those are the distances to the center. So I'm going to change the bottom of each to A squared, A squared, A squared. And there's a K and there's an A squared in every possible term. Okay? So I might be able to factor that out later. But the Q1, the R1, the Q to the R2, the Q3, the R3, those are different. All right, let's put those in now. So we're going to have K times positive 2Q over A squared, and that's R1 hat, plus, and then we have K times negative 2Q, and that's all over A squared, and that's R2 hat, and then plus, and then K times negative 4Q over A squared, and that's R3 hat. Okay? So now I'm going to go ahead and factor it. It does save me a lot of work later. Actually, do I want to do it now? Actually, I don't know that I want to do it now. Actually, so let's just go ahead and not worry about factoring yet. I want to focus on the R1, R2, R3. Okay, so Q1, the R hat vector points from the actor. So don't think of that as that's not a field line. That's a R hat vector, different, okay? And that thing is clearly pointing in the 240 direction, right? It's pointing in the 240 direction. So for R1 hat, I'm going to think of that as cos 240 sine 240. Or it's the teensy-weensy vector negative half negative root 3 over 2. Okay, let's look at R2 hat. R2 hat also points away from the actor, which is in this case Q2. And that one's clearly pointing in the direction 300 degrees. So see how it's pointing down and to the right? Okay, so that's going to be in the 300 degrees direction. So that's going to be cos 300 sine 300. In other words, it's going to be 1/2 positive and then negative root 3 over 2. And lastly is R3. R3 points from the actor, right, from the actor down here. And R3 hat is pointing in the direction 150. It's not directly to the left, it's slightly up and to the left. That's your direction 150. So that's cos 150 sine 150. I won't write it out. It's just negative root 3 over 2 comma half. Okay, so that was kind of a lot of work to figure out those, but now we can insert those down into our work below. So I'm kind of out of space, but you don't have to erase. You can just fill in, another line, but I need to erase a little. I'm going to put in my 3 vectors in component form right into here. Okay, so we have negative half, negative root 3 over 2. That's R1 hat. Okay, and then we have the other one, which is 1/2 negative root 3 over 2. And then our last one, which is negative root 3 over 2, 1/2. Okay, now I want to have you pay attention to the like terms. Okay, so it's a little bit hard to manage all this, but you're going to do basically outside red times first green plus outside red times first green plus outside red times first green, and that gives you your first component of the net field. Okay, so it's going to look like this. Okay, so I'll highlight it. Outside red times first green, so that's going to be negative KQ over A squared. And then we have plus, and then outside red thing, times first component. And you might say, Mr. Shore, you forgot your absolute values. I've decided on this problem not to use the absolute values. In other words, I was not really using a full free body diagram idea. I wasn't focusing on point K so much. I'm just focusing on R hats, which is sort of another way to think about it. You can certainly use the absolute values if you want, but what happens then is you have to remember to draw your field lines towards negative charges and then away from positive charges. The way I've done it, I've drawn my 3 R hat vectors always away from the charges. So by doing that, I do need to include the charge signs. Okay? All right. So anyway, I'm trying to add up the outside red times first component. So I have 2 more of these. It's negative KQ over A squared again. And then we have a positive 2 root 3 KQ over A squared. Okay, so why do we get a negative and then a negative and a positive? The reason is of the symmetry. Okay, there's 2 fields. There's so sorry, I interrupted myself there. what I'm trying to say is, why is it negative, negative, positive? It's because if you kind of go back to the idea that positive charges, fields lines are drawn towards themselves, negatives away from themselves, and negatives lines are drawn towards themselves. This one's going to produce a leftward component, and this one's going to pull in a leftward component, and this one's going to pull in a rightward component. So that's why when we did charges 1, 2, and 3, we got a positive, negative, negative, which I think I said that wrong. We got a left, left, right, which is negative, negative, positive. Okay, so sorry if I'm distracting you. We can just go back to the math, but things are going to work themselves out, is what I'm saying, because we've been very careful with r hat directions. Okay, now it's time to look at the y component. So it's outside times y plus outside times y plus outside times y. So we end up with negative root 3 kq squared over a squared, or kq over a squared, negative root 3 kq over a squared. And then in the middle, we have another identical one of those. So I'm kind of running out of space. I'll just keep writing. Negative root 3 kq over a squared. And then the last one is also a negative, but it's a 2kq over a squared. So I'll write it above here. Okay, and there's a bracket, which I can't seem to fit. Okay, so why is it negative, negative, negative? So again, it's going back to our charges. This is a positive charge. This is a negative charge. This is a negative charge. So when you draw your field lines in the vertical sense, these are pointing down, right? Because it's pointing out of the molecule, out of the charge, right? So it'd be pointing down. And then, if you're at P, at P, you would, or at point K in the middle, I mean, you would see it coming down towards you. And then over at the negative, the field lines are pointing in, right? So we're drawing the vertical ones. So we're going to draw one going up there. So I'll redraw. This one's coming out and down from the molecule. And then the charge 2, which is on the upper left, is pointing up and towards the negative. And then lastly, we have the bottom right there. That one's field lines are drawn towards it because it's a negative charge. So that one's pointing down. So that went going around. It's down, up, down. Down, up, down. Ooh, so that means I should have had a positive right here, I think. Let me just double check. Positive right there. Let me see. Did I make an error? Yes, indeed. If you look back at my math, I did indeed make an error there. So that's very important. You can see negatives in vectors are a big deal, right? They're really, really big deal. Okay, so our answer, we were able to validate it using the concept, right? You can always validate your math using the conceptual reasonability arguments. Okay, so let's pull out a KQ. Well, first let's combine like terms, then we'll pull out our KQ. So it's going to look like this. Negative 2 plus 2 root 3, and Mr. Short forgot to write his KQ right here. There's a KQ and everything, right? So it's negative 2 plus 2 root 3 KQ over a squared, comma, and then you have basically these canceling out because they're exact opposites, and then a minus 2kq squared over a. This should be, that's a bracket, not a square. Minus a 2kq over a squared. So assuming I combined like terms right, and I think I did, you could now basically just pull out the kq over a squared. So I have negative 2 plus 2 root 3, comma negative 2. So these are very, very, very advanced problems because of the vector thing. Now, once you get pretty good at it, you can kind of see what's going to double up and what's not going to double up. And you don't have to use my r hat method here, okay? Ultimately, there are a total of 6 arrows, 3 pointing left or right, and 3 that point either up or down. And some of them combine and some of them cancel. You're going to have to find your own way with vectors, but this is kind of how I think. I think in terms of unit vectors, okay? All right, so there is your final net field. And remember how we found magnitude and direction before. You would just basically do an inverse tan for the direction, and you'd use a magnitude square and sum and square root to get your magnitude. So I'll do it real quick, but I don't want to get too carried away with it. Okay, so to do the magnitude, you're going to do square root of negative 2 plus 2 root 3 squared plus negative 2 squared. So the magnitude, I went ahead and typed this one because it got a little awkward with the square root inside of square roots. You have basically 2.479 is a good coefficient there. And of course, that's not the actual magnitude. The magnitude has the kq squared over a squared, kq over a squared, right? So I need to write 2.479 kq over a squared. And this would be measured in newtons per coulomb, right? That's our new unit for the day, newtons per coulomb. Okay, that's the total, or the net E field felt at point K. Now, which direction does that E field point? For that, you use the inverse tan. Inverse tan. So you go for direction, you do inverse tan of y coordinate or y component over x component. And do we or do we not add the 180? Well, that depends on if the bottom is positive or negative. 2 root 3 is 3.4, minus 2 is positive. So we're not going to add the 180. In other words, I suspect my net field is actually going to be either quadrant 1 or 4. So then you would just type the remaining calculation into your calculator. So negative 2. You probably don't need the negatives. Well, yeah, you do, because there's a negative and a positive on the bottom. So just go ahead and type the negative 2 on top over negative 2 plus 2 root 3. So I'm typing it now. Not adding the 180, and just double checking that I typed it right. It says negative 53 degrees. I don't like negative angles, so I'm just going to push plus 360. 306.206. So basically 306 degrees direction. Okay? Notice again that because they, for some reason, in these books, often don't tell us what Q is, we just have to live with that, and knowing that Q is to be measured in coulombs and A to be measured in meters, you're going to end up with newtons per coulomb in the end, only if you know those numbers. K, by the way, I've told you this before, K is 9 times 10 to the 9th. 9 times 10 to the 9th. Or you can be more accurate by using 8.99 times 10 to the 9th. All right, so that's a pretty beastly problem.